Assalamu alaikum, brothers and sisters. Welcome to the Journey of Quest, where we quench your thirst of knowledge. Have you ever wondered what happens to geological structures and tectonic plates when immense pressure is applied to them? Why do they shift, reshape, and even rupture? Welcome to the captivating world of geodynamics and plate tectonics, where pressure, that invisible force, can cause massive shifts in the Earth's crust. Picture yourself standing over the Grand Canyon, observing the results of millennia of pressure and movement. Or consider an earthquake. With immense force, the Earth's plates can shift and shake, drastically altering the landscapes above. These natural phenomena are examples of the extreme kinds of pressure at work in our planet, leading to the creation of mountains, valleys, and ocean trenches. But what's truly happening beneath the surface? Why do tectonic plates shift or fracture under intense pressure? Is it merely about the application of more force? Or is there some deeper explanation? The answers lie in the intriguing study of geodynamics and plate tectonics. To comprehend this, we need to delve deeper into the theory of plate tectonics and the forces at work within the Earth's crust. Imagine Earth as a giant puzzle, with each piece moving and interacting with the ones around it. These puzzle pieces, or tectonic plates, are in constant motion due to the heat and pressure of the Earth's mantle. The pressure exerted on these plates by the molten mantle, and their interactions with each other, manifest in the form of stress. In the realm of geology and earth science, stress isn't about emotional tension, but is a measure of the internal force that the Earth's crust experiences when external forces, such as the movement of tectonic plates, are applied to it. Simply put, it's the amount of force exerted on each unit area within the Earth's crust. The movement of the tectonic plates is akin to an external force, and the Earth's crust responds to this force with stress. The nature of this stress can vary, depending on the force applied. There's tensional stress, which occurs when the crust is stretched or pulled apart. This is similar to happens at divergent plate boundaries, where plates move apart from each other. Then there's compressional stress, brought on when the crust is pushed together or compressed, as in the case of convergent plate boundaries, where plates move towards each other. Lastly, we have shear stress, which comes into play when different parts of the crust slide past each other, much like what happens at transform plate boundaries. So, stress in terms of geological forces and tectonic movements is about forces being applied on areas. It's the pressure that's exerted on the Earth's crust and how it's distributed. You can't see this stress, but you can certainly calculate it, and, more importantly, you can see its effects: earthquakes, volcanic eruptions, and the creation of mountain ranges. In essence, is the internal force that the Earth's crust experiences due to the movement of tectonic plates, and it's the response of the crust to these forces that shapes our planet. Let's traverse back to our geological formations. When tectonic forces are at play, the landscape doesn't just feel stress. It also experiences a change in shape. This alteration is defined as strain. Visualize the tectonic plates as a colossal rubber band. When pulled apart by the tectonic forces beneath, it distorts, doesn't it? That's a type of strain, the deformation of a geological structure due to an applied force. Strain is not about the force itself, but about how Earth's crust reacts to that force, how it changes in shape and size. We can categorize strain into different types. The first one, as we've seen with the tectonic plate analogy, is elongation. This occurs when a geological structure is stretched or pulled apart, leading to an increase in length. Think about our tectonic plates again. If the tectonic forces are strong enough, the crust might stretch slightly under the pressure. The second type of strain is compression. Here, instead of being stretched, a structure is squeezed or shortened. Imagine if these tectonic forces decided to exert immense pressure on our geological structures. The stress could squeeze these structures, causing them to compress. Then we have shear strain, which is somewhat distinctive. It transpires when a geological formation is forced to deform in a manner that alters its shape, but not its volume. Envision a stack of layers of sediment. If the tectonic forces push the top layer to one side, the sediment layers maintain their volume, but their shape has changed. That's shear strain. So strain is truly a measure of deformation. It signifies the displacement between particles in the geological structure. But remember, it's not just about how much a structure can deform. It's also about how it deforms, through elongation, compression, or shear. The type of strain can enlighten us about the material's properties and how it will respond to stress. Thus, when we converse about strain, we're discussing how much a geological structure morphs in response to tectonic stress. As we delve deeper into this intriguing world of stress and strain, remember this: Every geological structure has a story to narrate, and strain is a significant chapter of that story. What's the connection between stress and strain in the vast landscape of structural geology and geotectonics? It's not as straightforward as you may think. To decode the stress-strain relationship, we must delve into the characteristics of the geological materials involved. Various rocks and minerals react differently to stress, introducing us to the concept of geological deformation. Geological deformation is the transformation in shape that rocks or minerals undergo when tectonic stress is applied. This can be classified into two types: elastic and plastic deformation. Elastic deformation is akin to a geological fault that only moves during an earthquake. Some stress is applied, the fault shifts, but once the tectonic stress is removed, it reverts back to its previous position. The slip and slide of tectonic plates, the rebounding of the Earth after an ice age, these are perfect examples of elastic deformation. Plastic deformation, conversely, is a lasting change. Picture it as the slow and steady shaping of mountains. You apply geotectonic stress and transform its structure. It remains that way even when the tectonic stress is removed. The warping of layers in a syncline, the shifting and bending of rock strata over eons, these are demonstrations of plastic deformation. Now let's call upon a character from the annals of physics, Robert Hooke. Hooke's law, even in geology, states that stress is directly proportional to strain up to a certain threshold, known as the yield point. So, as you apply more tectonic stress to a geological structure, it deforms or strains more, but only to its yield point. Beyond this point, the structure may start to experience plastic deformation. It's like the slow bending of the Earth's crust. Eventually, it won't revert back. This stress-strain relationship, and the determination of the yield point, is vital in predicting how geological structures will react to various tectonic conditions. Will it rebound like an earthquake fault, or will it stay warped like a mountain range? Keep in mind, the stress-strain relationship is a key aspect in predicting how geological structures will respond to varying geotectonic circumstances. So what does the understanding of stress and strain mean in practical terms? Let's revisit the significance of understanding these principles. Stress, an unseen but potent force, is the pressure exerted on an object. It's the force that has the potential to alter an object's shape or even break it. Strain, conversely, is how the object reacts to this stress. It's the change or shift that occurs due to the force exerted. Comprehending these notions is crucial, especially in the realms of engineering and geology. How so? Because it enables us to foresee how materials will react under varying conditions. This knowledge becomes indispensable when creating and assessing structures for safety and longevity. Suppose you're a geologist predicting an earthquake's impact. You'd need to calculate the stress exerted on the Earth's crust and the ensuing strain. How much deformation will occur, and will it resort back to its initial state once the stress is removed? This understanding aids in estimating the magnitude of geological events and designing buildings that can resist these forces with the right balance between strength and flexibility. Similarly, it's applicable to everything from skyscrapers to your mobile device. All these require materials that can endure the stress they'll be exposed to, and that can respond with the appropriate level of strain. Therefore, though stress and strain may seem like remote concepts, they are actually inherent to our daily lives. Their interaction is perpetually molding and remolding our world, from the most monumental structures to the tiniest devices. The next time you witness a geological event or a towering ponder, the stress and strain that contributed to its formation. It's all woven into the intriguing sphere of materials, science, and geology. Thanks for watching us share our videos, subscribe our YouTube channel, and press the bell icon, and stay curious for new uploads.